The gang is splitting up for today. He's the one he gave back. Question. Yeah. Question he put down C as the right answer, but that's the spending clause. I think what I'm trying to say is I think you actually got 12. And I think you got 4 out of 5 right then, because I don't know if you have this quiz, but essentially I did, yeah. I was like, hey, this stuff. No, not yet.
Can you show me which one is it?
That was on the.
I mean, I told him like.
Yeah, this was one was.
He says, okay, so the whole process. That's what I'm hoping. But he says the right answer is which has to do with taxes. It's not right. Yeah, it's not right. So I choose A. Most people put A. Yeah. Yeah. So no. He doesn't. The scan. Right here. But really, I think you got maybe. I don't know if the answer to that is A or B. I don't know. But I think there's an issue. So no one got a first grade, which is why we'll see you tomorrow. We'll find out.
Today we got today's stuff.
I don't know what way to go.
That was oh, okay, that's what I saw it. Oh.
Okay, so for today, I want to talk about a bunch of common distributions. Before I do that, though, I want to say a couple words about the homework. I want to finish the app shop case, and then we're going to sort of learn, make sure we know all the distributions on this table. Some you already know, some should be familiar, some are new. So a few words about the homework. The first one was, what was my purpose in question 1? My purpose was to make sure that everybody knows exactly what Excel is doing when they're building a histogram. So main thing to notice was that the numbers you got using your count if statements when you constructed it manually should have been exactly the same as what Excel gave you when it produced the histogram with the defined bits. There was a question at the end that is probably worth some discussion, and that was what assumptions are you making? So why don't you guys tell me some of the assumptions you're making when you're taking data and you're doing a histogram plot of it?
That the data is that your sample is actually representative of the population, and that the minimum and the maximum are going to make sense as like a true minimum and maximum for your population.
So one is my data is representative of population. One is I'm going to be a little bit careful if the minimum and maximum of my data are really representative of the minimum and maximum that I could possibly get for this distribution. What else?
In this case, it was a singer, so you are actually assuming that this is indicative of traffic. So if after you ran this equation, the singer has an enormous scandal that drops their numbers, then your data is useless.
Yes. So every time I'm doing a histogram, I am thinking that past performance is indicative of future performance. Definitely.
For that one, you assume that because you're selling out different nights to accommodate for the fact that the demand was like more than 200 each time, you're assuming that each consecutive night will fill up until the last one.
Yeah, so people don't have preference for one night over the other. I'm treating Saturday night the same as Monday night, which is perhaps not quite accurate. But I kind of want to go back to, before I answer you, I want to go back to the past performance not indicative of future performance. Can I say something a little bit stronger about that? What if singer X has been getting more and more popular, or less and less popular in the past year or 2 years? I'm treating all these data observations exactly the same. If there's any trend in this data observation, I am not accounting for it. So I think one important thing to know when you're doing this is you're really assuming there's no trend in the data. There's like some randomness in the data that you don't know how to account for, but it's not like singer X has been growing and growing and growing in popularity, or vice versa has been declining in popularity. Is that what you're going to say? Or?
Yeah, I was going to say geographical popularity is as popular in Southern California as maybe the other continents or the Northeast or abroad. But I guess also that not a single person wants to go to the concert the first night, also wants to go to the second and then the third. That they're just like a one-time concert tour for singer X.
Yeah, so I'm treating all days identically, which is not quite correct. And also, let me say a little bit more about the geographic, right? So you pointed out that I'm treating all geographic locations equally. What if there's a hurricane out on the southeast coast? You know, that probably means that that's going to affect Florida, it's going to affect maybe some of the Carolinas, maybe it's going to affect Georgia, maybe it's going to affect New Orleans. So that means maybe there's some correlations between how much these singers' concerts are going to sell, because if there's a hurricane and nobody comes. So I'm also ignoring any correlations in the data. I'm basically treating all of these different cities as independent. And when you're doing histogram plots, you're generally treating your data observations as sort of independent in some sense, because you're not really accounting for correlations between different observations.
So how would you, so when you're actually trying to create this kind of you would make those modifications to the individual where you can modify data to something to run the histogram, or would you just have to make the histogram fit those assumptions?
Whenever you're making a histogram, you are making it with those assumptions. How can you get around it is, well, A, maybe make sure that if you think there's an upward sloping trend, don't use all of the data, just use the last 6 months, not the last year. So one way you get around it is by, you may not always want to use all of your data for this method. There are other methods, there's time series methods not going on in this class that will sort of try to let you account for both dependencies and time trends when you're looking at what happened last year and you're trying to use that as what happens this next year, but we're not exactly going to talk about that, but the histogram is not taking that into account. It's a little bit of a wandering answer. But ultimately the answer is just be aware that that's one thing that you're assuming when you do the histogram, and if your data set doesn't satisfy it, sometimes what you can do is you can split your data set up into parts where parts of it do satisfy it. Like for correlations, maybe you say, oh, I want to do the Southeast on its own and California on its own because I feel like those are sort of separate populations. So that's one way to handle it. But you have to think about that a little bit in accordance with the particular data you have. Question 2, I actually wasn't going to say anything about. We did something very similar in class. I'm posting the solutions today, so for the specific numbers, you can go over it. I've done it in 2 different ways. I've done it graphically using a tree, and I've done it using the Bayes theorem and definitions of conditional probability we discussed. So I'll let you do that on your own time. Question 3 I did want to talk about. In some ways, I felt like question 3 maybe was kind of the most thought-provoking. And the purpose of question 3 was to relate between this kind of abstract definition of independence that we got, and what does it mean when you look at a data set and you try to decide whether or not 2 events are independent. And so I gave you this sort of small data set so that it was very easily workable. And I want you to remember that we said if 2 events are independent, one thing we know is the probability of E1 intersection E3, so E1 and E3 occurring together, should be exactly equal to the probability of E1 times probability of E3. So multiplication and independence are just intricately intertwined. So let's go to this data set, and let me ask you, in this data set, and how do I read this? So I read this, I look at E1, And it's like I have 10 days, and I know on the first day E1 didn't happen, second day E1 didn't happen, third day E1 didn't happen, fourth day E1 didn't happen, all the way out to the 9th day it didn't happen, and the 10th day it didn't happen. So if I'm going to assess a probability for the occurrence of E1 based strictly on this data set, what am I going to say?
20%?
Yeah, 2/10. And you're definitely giving me something that's non-negative. So I would say in particular, the major thing I want to point out there is you saw E1 occurring, so you know you don't want to assign it 0 probability. What about E3? And the same thing, you definitely don't want to assign it 0 probability. What about E1 intersection E3? 0. You have never seen, in this data set, you have never seen a 1 for E1 and a 1 for E3 at exactly the same time. So your best estimate of the probability that E1 and E3 occur together is 0. But over here, you've got some positive number for E1, you've got some positive number for E3. You are never going to satisfy that equation. So based strictly on this data set, you're going to tell me that E1 and E3 are not independent events because they do not satisfy the definition of independence. How are you thinking about that intuitively? Why intuitively should these two events be independent? Well, if I tell you E1 happened, and you know that every time in this data set you've never seen E1 and E3 happen together, if I tell you E1 happens, that tells you that E3 is not going to happen. So that means that if I tell you something about E1, you're getting a lot of knowledge about E3. So there's no way that's independent. Now you can definitely argue with me that 10 is not enough observations, and if I have 1,000 observations, just because I didn't see E1 and E3 occur together in this particular data set, maybe in 1,000 observations they eventually would occur. Yes, I completely agree with you. That's a very valid criticism. I gave you a small data set just to make this point about what does it look like when you see in your data what might independence versus dependence look like. That was the point I was trying to make. I definitely agree with the criticism that this is a small data set. Okay, and the last one, it's probably easiest to look at my answer when I post it. But how do you think about this? The one thing I should apologize for is I realized that the solution in the textbook was actually a lot harder than the question, so I think a lot of you struggled to go through the solution, and I should have given you a pointer that you really didn't need all of the stuff going on in the solution in the textbook to answer this question. I just didn't realize that until late. So fire location is out here. We've got this town kind of like an old western where it's just a one-lane town, and the fire can occur anywhere between 0 and L. This is where the truck is located, it's out here. So our distance that we have to travel to the fire is 1.2 minus x, if I'm letting x represent the location of the fire. So this is my random variable associated with distance that I have to travel. And if I want to make a calculation like the probability I travel less than or equal to L over 3, well, the probability 1.2L minus x is less than or equal to L over 3. So I can do a little bit of algebra. That's the same thing as the probability that 13/15 L is less than or equal to x. X is perfectly uniform, so we're all equally likely to occur that location anywhere between 0 and L, which leaves me 2/15 probability that it occurs past location 13/15 L. And you can do the others in a similar. Okay, so that was homework. Next thing is I wanted to finish the abstract case, and I felt like we didn't quite have enough time last class to sort of make sure everybody's Excel file was working. I went ahead and posted my Excel file, so I think it's easiest just to make sure we're all on the same page, that we all just start out with the same Excel file. And I want to explain what's going on. So we had this case, this is from the beginning of class, we've seen it umpteen times now, and we're trying to calculate the expected value of this RFP. And the distribution the case gave us was triangular. We didn't know how to handle triangular at the very beginning of class, now we do. And I've just graphed this for you. So this is the CDF of a triangular distribution. The case told us triangular was, it was triangular with parameters minimum value 3.2, maximum value 12.8, which is why it's 0 below 3.2 and 1 above 12.8 in this graph. And most likely value 5.6. So 5.6 is where you can't really see it, but there's a change in the slope line. Now, what happens at 5.6? So let's just think about this 5.6. If I look at the value, f of 5.6, that comes out to 0.25. And let's think about my algorithm. My algorithm, and I always start out this way, is if I want to create samples from any continuous distribution in the universe, I'm going to start out and I'm going to generate RAND in Excel. And that's between 0 and 1. So that's a probability. And it's giving me something on this y-axis between 0 and 1. And, you know, if I get something below 0.25, if I get something below 0.25, then it is this equation that defines the relationship between the u, the RAND, and the x that I want to return. The x that I want to return is something between 3.2 and 12.8. And if I get a u above 0.25, then it is this guy that defines the relationship between the u and the x that I want to return. Okay, so that gives me my algorithm in Excel, and it says I'm going to generate my uniform. If the RAND's below 0.25, I'm returning this guy. This guy I'm basically solving for x in terms of u, so 23.04, I'm taking a square root of 23.04 times u, I'm adding 3.2, so I'm getting this directly from this equation. And otherwise, I'm returning, again, I'm getting this directly from this equation by solving for x. Okay, so if you open up my spreadsheet, so B is my RAND. You look at column C is implementing exactly this statement in Excel. And we've already done this case, we just did it with a uniform, right? So I'm just replacing that uniform distribution for the savings with a triangular distribution for the savings that the case actually asked us for. And so I'm replicating these different savings 1,000 times. Everything else is the same. And you can see up here, when you go to calculate your mean net present value, it's 0.52. Now, maybe you're sitting there and you're saying to yourself, well, okay, this is all well and good, but did I really produce savings distributions from a triangle? How do I kind of double check myself? And maybe I should pause for just a minute first. Are we good with this spreadsheet right now? Okay. Okay, so now the question is, how do I double check myself that I really am generating these savings distributions for triangular? Because clearly if I'm not using the right distribution there, I'm going to be getting the wrong answer. And one issue, and somebody asked me about this last Monday, so thank you, I can't remember who, but you inspired this discussion that's about to happen right now, which is, so what's this difference between the CDF and the PDF, and when I'm producing these histograms, like, what does it mean? Well, you know, when you double check yourself, I suggest that you double check yourself with a PDF, not a CDF. Why? Well, the issue is all these CDFs look similar. What do I mean by that? Any CDF in the entire world, it starts somewhere at 0, depends on where the minimum value of the distribution is. It stops somewhere at 1, depends on the maximum value of the distribution. And it kind of curves a bit between 0 and 1. And to the eye, how this curve looks, boy, to me that looks a lot like a normal distribution, in a way. So these curves can be hard to differentiate between by the eye. So that's why I'm suggesting that you use PDF instead of CDF. PDFs tend to have more distinctive shapes. So triangular is named triangular because the PDF looks triangular. So when you do your histogram plot, you should be getting something that sort of looks triangular. And I would say it's just like it's not a statistical test, but it's your gut level, do things smell right test. Your histogram plot should sort of be consistent with the distribution that you're trying to simulate. And your mean and variance should be consistent with the distribution, or mean and standard deviation. And one nice thing about working with these named distributions is, based on the parameters, we know the mean and the standard deviation. And so we saw the triangular a little bit. How do I calculate mean of triangular? So mean of triangular, it's known, it's a formula. Triangular is parameterized by three things. The A is the minimum value, the C is the maximum value, the B is the most likely value. So the B is this point here. And the mean is to add these up and divide it by 3. And there's a formula for the standard deviation too, a little bit more complicated, but I can do it. I can plug in our A's, our B's, and our C's, and I get a 2. So now you can go to my Excel file, and I wanted to double check myself, so let's double check if we're really generating savings from a triangular distribution. And so first thing is the mean, so I can just check the mean. So the mean is looking at the average of those values in column C, and you can notice it's pretty close to 7.2. You can press F9 to generate a few different samples, and it fluctuates a little bit, but it's certainly staying around 7.2. And you can do the same thing with the standard deviation and observe that it's staying pretty close to 2. Not exactly, but this gives me some confidence that I'm doing the right thing. And you can also do the histogram plot, and the histogram plot, you know, it's never going to look exactly like this, but you can certainly see that it looks a little bit triangular up here, and if I kind of draw some lines, it looks a little bit triangular here versus here. The reason I'm thinking it's not a normal distribution is there's definitely a skew to it, right? There's a skew in that the right-hand side here is looking a bit different than what I'm seeing on the left. So it's not a perfect, this is never an exact science, there's a little bit of an art, but all of these things are suggestive to me that yes, I am really generating the right distribution. And like I said, there's some statistical tests you can do, we'll talk about them a little bit later on, assuming we have time. But at a just gut level, this passes my reality check. Okay, and so I would suggest whenever you're trying to simulate a distribution, this is probably a good thing to do just to make sure that what you think you're doing is what you're actually doing.
Sorry if you said this and I missed it, but for the formula for the PDF, did you just take the derivative?
Yes, I didn't say it. I just gave it to you and had you take it on faith. It's always PDF is derivative of CDF and vice versa. And to be clear with what I expect is I'm not going to be focusing on can you do the derivatives and integrals. You will sometimes see me doing them, so I just need a little bit of familiarity with what that is. But yes, that's exactly right. Okay, so then I said we're going to learn some common, discrete, and continuous distributions. And so let me start with discrete. And really everything's based on coin flips. So I'm not going to motivate everything with the greatest stories in the world, but remember your motivation is essentially what you want is you want the power to know a bunch of name distributions. These are probably the most common, quote, name distributions that come up. So you can kind of look at your situation, you can look at histograms, you can kind of decide what's the right distribution to use for modeling. Okay. And, okay, motivation is you're going to have data, you're going to do histogram plots. We want to be able to think about what distribution does that look like, right? Because if it's a distribution that is a quote name distribution, then that makes life easier. Okay, so Bernoulli is the first one. Bernoulli was a man, so it's named after a man. And it's a coin flip. So flip a possibly biased coin. It's 1 if the coin lands heads, it's 0 if the coin lands tails. And all of these name distributions are parameterized. So when I say parameterized, what I mean is I'm giving you a P. If you tell me it's a Bernoulli distribution, you can't just tell me Bernoulli, you need to tell me Bernoulli of P, and P is telling me the probability we land heads. And what are examples of situations in which Bernoulli arrive? Well, this is basically an experiment that has exactly 2 outcomes. So let's say I own a store, a customer walks in, they either are there to browse or they're going to buy something. 2 outcomes. And mean and variance, you can make this calculation population yourself if you want a little practice with mechanics. Otherwise, you can trust me. And we're actually not going to try this because I think we're pretty familiar with it. But how do you produce a sample from a Bernoulli in Excel? You're going to say if rand is less than p, give me a 1, else give me a 0. And this is going to p% of the time give you a 1, and the rest of the time 1 minus p, or q% of the time give you a 0. So what's a binomial? So a binomial is a sum of Bernoullis. So basically it is, let's say first I flip 2 coins, and x counts the number of heads. So what's the probability mass function for that? Well, let's think about it. There's 3 different things I could get. I could get a tail-tail, I could get a tail-head, a head-tail, or a head-head. And if I'm counting the number of heads, what's the probability I'm going to get 0 heads? So this is corresponding to the probability that x equals 0. X is the number of heads. What's that? Sorry.
1 by 4. 25.
Does it have to be a fair coin? Okay, so if it's a fair coin, I completely agree it's 25%, but remember I'm parameterizing this distribution so that it doesn't necessarily have to be a fair coin. So in that case, it is q squared. I completely agree with the logic, but I want it parameterized so it's q squared. I want the probability that x equals 1. What is that going to be?
Q times T.
The number of heads I get. So 1 is, what's the probability I get 1 head? Q, 1 minus Q, or P times Q, because P is exactly equal to 1 minus Q. And there's actually 2 ways I could get that, right? This one and this one. So that should be 2 times PQ. And the probability that x equals 2 is the probability I get the head-head, and that's a P, so that is a P squared. So that's my probability mass function. I could keep doing this. And in general, when I look at the binomial, it's parameterized by 2 things. It's parameterized by this P, this probability that I get a head, and an N, which is the number of coins I flip. I didn't have to limit myself to 2 or 3. So I flip N coins, I count the number of heads. What are situations when this arises? Drug trials. You give out drugs to 100 people. You're looking at, for each person, whether or not the person responded favorably to the treatment. You own the store, 100 customers come in a day. You want to know, well, what's the proportion that actually bought something versus the ones that browsed? So anytime you can figure out something where you've got, okay, I got exactly N trials, and each of these trials are going to be a 0 or 1, you've got a binomial. And there's a general form for the probability mass function, which I'm going to let you take on faith here.
So there's a difference between Bernoulli and binomial that binomial has to be the 50% and 50% tail?
No. So both have the exact same parameter P as the probability something comes up as 50%. The binomial you can think of as summing Bernoullis. So if I flip 1 coin, it's a Bernoulli. If I flip N coins and I count the number of heads, I'm basically summing the number of heads because the head is a 1. That's the binomial. Okay, and so this is the probability mass function. Factorial, n factorial is n times n minus 1 times n minus 2 times n minus 3 all the way down to 0. And, you know, let's say you're looking at this and you're like, well, I just kind of want to double check. What is this probability mass function? What should it be? That looks a bit crazy. I don't know how to deal with this. You can do this in Excel too. So let's go ahead and open it's the one called binomial. And let's think about how if I want to calculate probabilities of this binomial, and I think that's looking a little yucky, how might I calculate probabilities? You know, I can do a simulation for this. So what are you looking at? Let's take, this is the flip, so this is my trial basically. And I'm flipping 4 coins. If n equals 4, I'm flipping 4 coins. And let's say p is 0.5, so I'm flipping a fair coin. So coin 1, if rand is less than a half, you have this spreadsheet, so I'm assuming you can see everything. If rand is less than half, I'm giving it a 1, else I'm giving it a 0. And I'm doing that 4 times. So I'm simulating 4 coin flips, and the number of heads is I'm just summing. And I want to produce this probability mass function. I've done this 1,000 times. So the probability that x equals 0, what am I doing? I'm counting the number of times that that heads comes up as 0, and I'm divided by 1,000 because I have 1,000 tries. So I'm creating my own probability mass function. So this is one way to simulate your binomial. And it's probably useful to see the connection between the formula here and the numbers we just got here. So let's look at this in n equals 4. If n equals 4, and I want the probability I get 0 heads, so this is telling me n choose I, and what is this? So this is 4 factorial divided by, the I is the 0, so 0 factorial, 4 minus 0 is still 4. And this is p to the I, 1 minus p to the n minus I, so this is 0.5, my I is 0, 1 minus 0.5 is 0.5, and I have 4 flips. The 4's cancel out. By convention, 0 factorial is just 1, so this is a 1. So I'm looking at 0.5 raised to the 4th power, and what's that? That's like, whoop, 1 over 2 to the 4th, which is 4/816, or in decimals, it's about 0.0625. And I can make the calculation for P of 1, P of 2, P of 3, and P of 4, which, if you want me to do it explicitly, I will. Otherwise, I'm just going to give you the numbers and you can double check it. So P of 1 is 0.25, P of 2 is 0.375, P of 3 is 0.25, and P of 4 is 0.0625. Actually, since the coin is heads or tails and it's half, these guys, it's got to be symmetric at 1 and 3 and 0 and 4, so that's a good double check. And you can see over here, my probability mass function, well, it's not perfect, but it's close. How would I get it closer? I need more flips. But this idea here, where if I'm summing random variables, this is a sort of a nice way to calculate probabilities. That idea is can be useful. I'm summing Bernoulli's. I'm summing in Bernoulli's. So mean n times p, variance n p times 1 minus p. Notice for the Bernoulli, the mean is p, the variance is p times 1 minus p. I'm summing Bernoulli's, I'm summing them n times, so I just get to multiply by n. Is geometric. So again, I got this biased coin. So for the first 3 distributions, they're all dealing with this biased coin. And I'm looking for the first time I get a head. So I'm flipping it, I'm counting the number of flips until I get a head. And what are examples of situations where this might rise? So if I own this store and I'm counting customers and I'm counting the number of customers that come into my store until the first time somebody buys something and doesn't just browse. This is the probability mass function. So I have to have I minus 1 times where I got a tail, and then I'm multiplying by the last time where I got a head. And there's only one way that could happen, so that's sort of the explanation for the PMF. And I'll let you to take me at my word on what the mean and variance is.
It's like the discrete version of exponential.
Yes, this is exactly like the discrete version of exponential. And in fact, I'm going to skip ahead. So if you look at our two distributions that I gave you two example histograms, what does the geometric look like? Looks an awful lot like exponential, right? That decay is it looks kind of like exponential. What's the difference? In some situations, it's going to make sense to have continuous. In other situations, like when we're counting coin flips or we're counting people, it's very clear that you don't want any fractions. You want 1, you want 2, you want 3, you want 4, you want positive numbers. So that's how you would tell the difference between geometric and exponential. But yes, that looks kind of exponential, except it's exponential on the integer numbers. This one over here, we've done geometric and binomial. This is kind of what the binomial looks like. So for this one, I have a p equals 0.2. You notice it's slanting a bit towards the right side, so the p is controlling whether or not you're getting sort of something symmetric, or whether or not you have some kind of skew in the distribution. And by skew, I mean values here that are low are much more likely than values up here that are high. So that's kind of what these two distributions we just talked about. Okay, now to go backwards, mean and variance. I'm letting you take me at your word at that, at my word at that. You can definitely double check the calculation. This idea of summing is nice because we get a lot of distributions for free. So negative binomial is another one we get for free. I'm thinking we get binomial for free because we're summing Bernoulli's. We get negative binomial for free because we're summing geometrics. It's an awful name. At least I think it's an awful name, but whatever. What does it mean? We're counting the number of flips not until we see the first head, but the kth head. Okay. So this is a sum of geometrics. So I'm counting not until the first time somebody walks into the store and buys something. I'm counting until the 5th customer that walks into the store and buys something. And so mean and variance. So kth geometric, I'm summing k geometrics. Mean of a geometric is 1 over p, so this is k over p. Mean of geometric, or variance of geometric is 1 minus p divided by p. I'm summing k geometric, so it's k times 1 minus p.
Can we just talk for a second? What are examples of situations in which you would see this in real life?
An excellent question. So first I have a few, a little bit contrived, and then we can talk a little bit more about the real life examples.
Okay.
So let's start with the contrived.
Right.
So number of days until you sleep through your alarm, what should that be?
Negative binomial.
Negative binomial with what parameter?
So basically, where k is like the number of days you don't either do or don't sleep through your alarm.
Geometric.
It's geometric. It's negative binomial with k equals 1.
Gotcha.
Or it's geometric because every day I'm flipping a coin, and I might sleep through the alarm, I might not, and I'm counting the number of days number of flips until I sleep through that alarm. How about number of no-show appointments in a doctor's office?
Binomial.
Binomial. So the doctor's scheduled 12 appointments throughout the day, however many he thinks he can handle, and when he's doing that, he's probably taking into account the fact that some people may not show up. So for his capacity planning, he's really thinking, oh, I have a binomial. Well, he may not be thinking I have a binomial distribution, but essentially he's thinking he's got a binomial distribution that's determining the number of people that actually show up versus the number of people that don't show up. And we're treating everybody as equally likely as a coin flip that they may show up, they may not show up. How about the number of calls a Clinton or Trump supporter, this is really for in the fall, I guess, has to make to obtain 5 donations?
Oh, okay. That would be negative binomial.
That would be negative binomial. So now I'm sitting here, we'll say I'm fundraising for USC. I'm fundraising for USC, I'm on the phone, I'm calling donors, I'm calling donors, I'm calling donors. How many donors do I have to call to get the first donation? That's geometric. How many do I have to call to get the second donation? That's negative binomial. How many do I have to call to get the 5th donation? That's negative binomial with k equals 5. Number of passengers that order chicken instead of pasta on an airline flight. Binomial. You've got 100 passengers on the flight. Each has a choice. It's chicken or pasta. So if I go to the real life, so first of all, the purpose of this is, why am I giving you this? I'm giving you, when you're looking at these histogram plots, you want to go from your histogram plot to having a bunch of distributions in your arsenal, and you can kind of go back and forth between what the histogram looks like and what you know about the distribution in terms of qualitatively when it needs to show up. Where do some of these show up? Medical trials is actually where you see a lot of binomial and Bernoulli. I think I mentioned that before. So you're giving drugs to a patient. Each patient is one trial, and you're looking at whether or not the patient responds to the drug. So that actually comes up a lot in the medical case, in medicine. Okay, so we've learned all the discrete except for Poisson, and the continuous you've seen everything but gamma. And the next thing I want to do is I want to talk a little bit about the continuous, and you've seen uniform and triangular, so I'm going to go over that reasonably quickly, and I'll end with talking about exponential and Poisson, because there's this nice relationship between exponential and Poisson. That's probably, I was going to highlight the class, it's a highlight of the class. Okay, so uniform we've seen, that's RAND in Excel, everything's equally likely. You're using it when, you can kind of think of it as modeling ignorance. You don't know anything, so you're just assigning the same frequency of occurrence to all possible values. It doesn't have to be between 0 and 1. So it could be anywhere between A and B. If I say uniform in A and B, that means every value between A and B is equally likely. A is minimum, B is maximum. And PDF, just 1 over B minus A. What's the mean? What's the variance? So mean should be A plus B divided by 2, right in the middle. Variance you can calculate, or you can take me at your word. So one nice thing about the parameterized distributions is once you identify the distribution and the parameters, you know automatically the mean and variance. And what's the median of this distribution? Same as the mean, A plus B divided by 2. I'm just as likely to be beneath the mean as I am to be above the mean. So it's very symmetric in that regard. So whenever you have symmetry like that, mean and median are equal. Triangular, this was the distribution in your case. I said it was parameterized by 3 values, so now I'm just emphasizing that. So there's 3 values. A is the minimum, C is the most likely, B is the most likely, C is the maximum. I've given you a few different examples. This one's symmetric, i.e. every point to the right of 10 is sort of the same frequency of occurrence as every point to the left of 10. The blue and the greens are examples of distributions where they're not symmetric, and you can see that reflected in the fact that your mean and your median are generally not the same. That's about the difference. Okay, then what about exponential and Poisson? So exponential and Poisson come up a lot with arrivals. So whenever you're thinking about customer demand and you're thinking about demand as arrivals to a web server or arrivals to your store or arrivals to your call center, that's when you're getting exponential and Poisson. And in answer to the real life example, I think arrival traffic is something that comes up a lot in our world, right? Because we want to know what's the type of arrival traffic that is coming in that we need to have capacity to make. Okay, so I'm going to motivate this with sort of a retail store demand estimation. And what I want is you to sort of discover for yourself why there's this dual relationship between exponential and Poisson. Poisson, which I haven't told you anything about, we'll just figure it out. And let's say you run a large grocery store that serves lunches, and it's in some pretty heavily trafficked location. Your busiest days are weekdays between, say, noon and 2. And you want to better understand the arrival pattern of your lunchtime customers during your busiest time. And you have 1 day's worth of data that shows arrival times of the customers to your store during your busy hours. So if I'm looking at, here's you. At 12:01 and 30 seconds, you're time stamping the first customer that passes through the door. Second customer passes through at 12:03, 30 seconds. Third one, 12:10, and so on. So that's the data I'm giving you. And the first thing we're going to be interested in is the random variable that's representing the inter-arrival times. So I want to know how much time in between these customer arrivals. What's the distribution of time I have to wait? Because I'm thinking, well, I have to serve these customers, so if I have to serve them, I want to know, like, how much time between one arrives do I have until the next one arrives? And so here, that's an inter-arrival time of 2 minutes. This is an inter-arrival time of 6 minutes, 30 seconds. So now let's go to our Excel sheet and let's figure out what's the distribution we should use to model this arrival traffic. And I posted arrival times. And actually, that's not the one I want, because it's already done. Okay, so I have arrival times Blackboard. And we can do this. So I already did this for you. I did the subtraction so that we know exactly what the inter-arrival time is of each customer. So in column B, I'm getting 12:01:35 minus 12:01 and 10 seconds, and that tells me that there's 24.85 seconds between those two customer arrivals. Oh, oops, thank you. And that tells me that there's 24.85 seconds between those customer arrivals. So I'm looking at, I want this distribution for each interval. So let's do a histogram plot. So we've done a lot of these. So data analysis, histogram. Okay. Input range is these inter-arrival times. Bin range is column E. And output range, let's say like G. And I want the chart output. And I'm going to say okay. And what does your histogram look like? Yeah, look like an exponential. Okay, so it kind of looks like these customers, if I think about the inter-arrival time, if I think about the time between customer arrivals, that's following an exponential distribution. So that's my observation number one. I've got an exponential distribution if I look at time between arrivals. And what's the mean? I also estimated the mean. It looks like there's 30 seconds. On average, there's 30 seconds between arrivals. That's just the mean. And the exponential is giving me sort of the variability around that 30 seconds. Oh. Okay, so here's my exponential distribution. You've seen it before. Exponential we're getting because we look at that form of the histogram, and the form of the histogram is definitely looking something like one of these lines. And the mean, you can't just tell me exponential. To know what exponential I want, I need to know the mean. So the mean of 30 seconds is telling me which of these lambdas to use. If I do this in minutes, it's half a minute. So according to my data, I'm really looking at this lambda equals 0.5. That's my goal line. And you can see that as I change lambda, what's happening as I change lambda? Well, as I change lambda, the mean time between arrivals is getting shorter. So that tells me that as lambda is increasing, I'm getting more and more arrivals. So this is the PDF. I'm graphing the PDF. This is the CDF. And what's the median of this distribution if I ask you for median? So are 50% of my arrivals coming in at less than 30 seconds? That would be another way of asking it.
Yes.
Is this a symmetric distribution?
No.
Not a symmetric distribution. So what does that mean? Mean and median aren't going to be equal. So mean is on average, every 30 seconds I have somebody come in. But 50% of the time, it does not mean that 50% of the time somebody is coming in, it's less than 30 seconds. So how would I figure out the median? I want to know, like, for example, I want to know 50% of my customers, for 50% of my customers, it's 20 seconds between the customer before them and them. How would I figure that out?
Look at the CDF up to 50.
Yeah, the CDF is telling me if the CDF equals 50%, so 50% is telling me exactly for what value I have 50% of the arrivals coming in before. Oh. So I've got 0.5 needs to equal the CDF, 1 minus e to the negative lambda x. In my case, the lambda is a half, but I'll solve it for general lambda. X, how do I solve for x? So this is 0.5, this is e to the negative lambda x equals 0.5. This is so x equals ln of 0.5. I've got a negative, and I got to divide by lambda. So this is my median, and whatever this, that's right. And whatever this median turns out to be, it depends on lambda. It tells me that 50% of the people are coming in 50% of the time. Somebody's coming in less than this number of seconds. Okay, so I'm just giving you an illustration where mean and median aren't equal because there's a skew. Okay, so what about this, I said something about this relationship, and there's sort of a dual to the explanation. So what we just did was clearly continuous, right? I look at how long is it going to take between my first arrival and my second arrival. It could be a second, it could be 3 seconds, it could be 1.235 seconds. It's definitely a continuous distribution. What's another way I could look at this data? Maybe I'm not interested in the times between arrivals. Maybe I'm interested in how many people come in. I want to know how many people come in a minute. I could ask that exact same question with this exact same data set, right? So let me ask what I'll call the quote dual question, which is suppose that instead of determining an inter-arrival time distribution, I want to determine the number of customers to arrive to my store every minute. So observation number 1 is that a discrete or continuous random variable? Discrete, right? I don't know how half a customer can come in. It's going to be 1 customer, it's going to be 2 customers, it's going to be 3 customers. Okay, so this is definitely discrete. It's different than what we were thinking about before. It's not continuous, it's discrete. It's counting a number of customers. What do I expect to be the mean of this distribution? Based on the data set I gave you.
I would expect it to be 1 over the average inter-arrival time.
Exactly. And we had half a minute as my average inter-arrival time. So it should be 2 customers that arrive every minute. If it's 30 seconds in between customer arrivals, it's 2 customers every minute. And that observation is one reason I'm calling this a dual relationship. So you can think of the exponential as giving you your rate of customer arrivals. You can think of the Poisson, the parameter here, is giving you your number to arrive in a particular time interval. Okay, but anyways, for this particular set, we should all agree that if I'm going to be consistent here, if I do some kind of count analysis to determine the number of people to arrive in a minute, I should get 2 arrivals per minute, right? That's what's consistent with this. Okay, so let's go back to our laptop and let's go to the count analysis. And the count analysis, in columns B and E, I just find times a little bit fidgety to work with in Excel. So in column B, I basically truncated all the times. And in column E, I'm just making sure that, so what do I want to do in column F? Okay, so I want to count every minute. I want to count how many people come in that minute. So in column F, I'm going to do equals count if of the data set I want is B. Shift control down. And the criteria is I'm looking for E2. And so here, E2 is like, you notice I've truncated it here. So E2 is basically counting the number of people that come in between 12:01 and 12:02, which is 2, you can see. And then if I copy down, put some, if I copy down and I look at cell F3, 1, so 1 is the number of people coming in between minute 12:01 and 12:02. So in column F, I'm generating every single minute, 12:01 to 12:02, 12:02 to 12:03, 12:03 to 12:04, I'm generating the number of people I see arrive to my store in that minute. Is that clear? Okay, so this is why I'm calling it a count analysis. And clearly, as we observed before, I don't have half a person arriving, it's always integers.
Are we doing Poisson right now?
We are doing Poisson right now, and we are about to do a histogram plot, and it's going to be a histogram plot of a Poisson distribution. So now we can do histogram plot of our counts. And if you look at my bins, I said, well, 0 people can arrive in a minute, 1 person can arrive in a minute, 2 people can arrive in a minute, 3 people can arrive in a minute. So that's how I'm getting the bins. And I'm going to do data analysis, histogram, okay. And so what's my data? My data is my counts. So this is my observations, or every minute, how many people do I see arrive? My bin range here. Is column H. My output range, let's put it, I don't really care, maybe J. And I'll say okay. So you're getting a histogram. It looks something like this. This is a histogram of a Poisson distribution. So when I have exponential inter-arrival times, if instead of doing the exponential inter-arrival, I do the count analysis like we just did, I'm always going to be getting a Poisson distribution on the number of people that arrive. And maybe our reality check is we already observed that the mean of this distribution should be 2, because the exponential was 30 seconds between arrivals, should translate to 2 people per minute. So let's also do that reality check. Let's just take the mean. So let's take the mean of my counts. And maybe you guys have already done that, but okay, so it's very close to 2. So that's why I'm calling exponential and Poisson sort of duals. If you see exponential inter-arrival times, then your count analysis is Poisson. That's always true. And these are just a few representations of different Poisson distributions. You can see it can be something that looks reasonably symmetric. It can be something that is very skewed. And what do you need to determine a Poisson? You need one parameter, you need to know the mean, just like the exponential. Why are these important? Very often when you're dealing with arrival traffic, you're dealing with Poisson or exponential. It's basically the same thing. If I tell you Poisson is a count, is number of people that arrive in a certain time period, you know in your head that is exactly equivalent to me telling you that it was exponential for time in between arrivals. And just to say that formally, Poisson exponentially relationship, suppose the inter-arrival time of events, for example, customers arriving to your store, follows an exponential distribution with mean of 1 over lambda. So this lambda you can think of as the rate at which events occur. Customers are arriving at rate lambda per time unit. Customers are arriving at rate lambda per time unit. The average number of events in a time interval should be lambda times t. And the distribution of the number of events that occur in that time interval should be Poisson, and the mean should be lambda times t. So the lambda is the rate that things are happening. Lambda times t is the mean number of things that should happen in any time interval. The distribution is Poisson. And if you look at today's example, we had time between customer arrivals was 30 seconds, 2 customers arrive every minute. This is often called the Poisson, well, let me give you a graphic depiction. I'll say what I was about to say in just a minute. So graphic depiction and pop quiz. Suppose you know the distribution of time between events, between customer arrivals to your store is exponential and it has a mean of 3 minutes. So here's time 0, and I'm just giving you a data set that marks every time I see an arrival. This is when I see the arrival. And on average, the time between those arrivals is 3 minutes. And now I'm going to do the opposite. I want to know, well, the next 10 minutes, how many customers are going to arrive? What's the distribution of X? Poisson, okay, so we know it's Poisson because I've been talking about this exponential do relationship, so it's definitely Poisson. What's the mean of that Poisson?
1/3.
1/3 for 1 minute, and I have 10 minutes, so it's 1/3 times 10,
So
which is
3
10
and
thirds for
3
10
and
minutes.
1/3. Yeah.
Okay, so we've got mean time of 3 minutes between arrivals. That means 1/3 person is arriving per minute. I've got 10 minutes, so 10/3 people on average are arriving in 10 minutes. And my Poisson distribution, I just need to give it the mean. Oh, and here's my graphic depiction. So we said on average 10/3 people are going to arrive. So here's 1 arrival, here's 2 arrivals. It's a distribution. I don't know, it's not always 10/3 people. That doesn't even make sense because it's a half a person. There's 3, there's 4. Okay, the 5th person is after time 10. So in this particular realization, I had 4 people arriving in the next 10 minutes. Maybe in the 10 minutes after that, I only have 2. So the average can definitely come out to be not be neutral. Okay, that's called a Poisson process. So if I ever say Poisson process, it's time between events follows exponential with mean of 1/λ, and the number of events in any time interval is a mean of lambda times t. And so that's used a lot to model arrival traffic. I said something about getting distributions for free. So gamma actually comes for free. That's the last distribution that was on my table. And gamma is sum of exponentials. So if I have a Poisson process and I want to know how long until the nth event, so how long until the nth customer enters my store, it's gamma. And this is basically 1 exponential for how long until the first customer comes. This is the second exponential for how long the second customer comes. This is the third exponential for how long the n equals 3/3 customer comes. And that total time is gamma. Okay, so I'm just summing exponentials. So I've got 2 parameters. This is n, the number of exponentials I'm summing, and this is lambda, which is the rate at which these events are occurring. And it's got this PDF. So what's the mean of a gamma? What's the mean of an exponential? It's on your slides.
And, 1/λ.
Yeah. So I'm summing
1/λ.
in exponentials. The exponential has mean 1/λ. So the mean time here for this first customer to arrive is 1/λ. Plus the mean time for this second customer to arrive is 1/λ, 2/λ. Plus the mean time for this third customer to arrive is 3/λ, right? 3 customers, each one on average takes 1/λ to arrive, so 3/λ, or in general, n/λ. Same thing with the variance. I'm summing. Variance of exponential is 1/λ squared. Variance of gamma is n/λ squared. So I'm getting this for free.
The
Yeah.
n isn't squared, right?
No, sorry, n/λ squared. What did I say?
Well, you said that, I was just making
Okay,
sure.
yes, the n is not squared.
Here, parentheses.
And the n should not be squared because 1/λ squared is the exponential variance, and I'm multiplying, I'm adding n of those. So. Okay, so now it's your turn. So I've got the in-class exercise on figuring out stuff about the gamma. It's potentially not the most real-life exercise in the world, but you can kind of imagine if you're thinking about arrival traffic, this gamma is coming up because it's time between event occurrences. So you're arriving to USC Credit Union ATM machine at the Student Center. There's just one of them. There are 3 people waiting in line. And we're counting the person currently using the machine. So there's 1 person using the machine, there's 2 waiting in line. And your sense is that each of these people is interacting with the ATM for 2 minutes on average. And how long, you're really excited because you have to come to your probability class, so you don't want to be late. So you're thinking there, can I get money? Do I have enough time? How long do I expect to wait to get my money? Wait, so this one should be easy. So 6 minutes, okay. So 6 minutes, there's 3 people, each one is taking 2 minutes on average, 3 times 2 is 6. This one is maybe the slightly harder one, is you're thinking, oh, well, you know, I got this 6 minutes to wait, so let's do another calculation. I really want to make sure I'm not late to my probability class, so let's say, what's the probability you wait longer than 8 minutes? So I really don't want to wait too long here, and 8 minutes is my absolute upper limit. So what's the probability I wait longer than 8 minutes, assuming that the time each person requires that this ATM machine follows an exponential distribution? And the hint is, A, you can do this in Excel, and B, the relevant thing that we did in class today was calculating probabilities for binomial, because I got a sum. And there's no free-form Excel, I don't have any sheet, you can just start on your own.
Are you saying that the average person does not interact for 2 minutes each time, that the first person takes 1 minute and 2 and 5 and 10?
No, I'm saying each person interacts on average for 2 minutes.
Even for the second one?
Even for the second one.
Okay.
So the first person is on average going to be 2 minutes with it, the second person is on average going to be 2 minutes with it, the third person is going to be on average 2 minutes with it. So you've got 3 people ahead of you, they're each taking 2 minutes on average. And more or less, the full distribution is exponential. Hint number 1 to get you started is, what are you thinking? You're thinking, well, if I want to estimate this probability, I have a really nice sum going on. The first thing you're maybe thinking is, if I wanted to write this mathematically, I would be writing it mathematically as the integral from 8 to infinity of that distribution. So the lambda is a half because it's, I said 2 minutes, so and the parameter is 1 over the mean, so 1 over 2 is a half. And so I'm putting in 1/2 e to the negative 1/2 t, 1/2 t. There's 3 people ahead of me, so my n is 3, so I'm squaring that, divided by, that's a 2 factorial, so that's 2 times 1 is just 2. So this is the calculation I actually need to make. And I'm saying, well, that looks a little bit ugly, but I promised you you could do it in Excel. And this is where, whenever you're working with continuous distributions, the integral under the curve area can be hard, but you can always simulate it. So this is a good example of where the simulation will help you out a lot if you don't want to do the calculus. And the hint is, you're thinking, oh, gamma is sum of exponentials, so that's nice. So I've got an x1, x2, x3. This is how long person 1 is spinning to the ATM. This is how long person 2 is spinning to the ATM. This is how long person 3 is spinning to the ATM. I have to wait for all of them. So I've got x1 plus x2 plus x3. Each of these are exponential. And oh, you know, in Monday we figured out how to simulate exponentials. Okay, so that's my middle of the in-class exercise hint. And now you get to set up your own simulation to figure out the probability.
is parameter specific, right?
Yes, it is parameter specific. So I mean, one nice thing about doing the calculation is I can get an in into the calculation, but
So when you're simulating it for like, especially for small number of things, like 3 people,
yeah.
it might not be that good.
No. That I disagree with because you can, you can get as many samples as you want. But I do agree that the limitation of the method is that it's always, you can only do it for one parameter. So if you, anytime I do the simulation, I'm specifying lambda, I'm specifying n. So I can't ask a question like, suppose the arrival rate changes a little bit, what does that mean for how much capacity I have to have? Or at least it's a little bit harder for me to answer. Not quite, so let me give a.
Don't do that?
Yeah,
Okay.
so
I
I'm
was
gonna
trying
give a
to
little
fit
bit
like X and a mean, but it sounds like that's about it.
easier way to do it, so I'm gonna.
Okay.
Okay, so I just wanted to know, like, yeah. Okay, so let's think about how am I gonna do this, right? So let me start you out on the Excel file. Okay, so here's the laptop, and I think here's the way to start this out, right? This is a simulation. The time at the ATM. So person 1 spends a certain amount of time, person 2 spends a certain amount of time, person 3 spends a certain amount of time, and my weight is the sum of these 3. And I know that each of these people is spending an exponential time. So what I need is a way to sample from this exponential distribution. And we actually did this in class on Monday. So I'm remembering Monday and I'm saying, oh, how do I sample from an exponential distribution? Well, let's look at this dot count. If I look at this exponential distribution, here's my x, here's my CDF, which is 1 minus e to the negative lambda x. In my case, the lambda is a half. And I know that if I want to generate this, I'm always starting out just saying rate. Okay, so here's my uniform. My uniform equals to rand. And I need to go from u, this probability, 0, 1, to what the x is. And I know what defines that, so I know that u has to equal 1 minus e to the negative 1/2 x. U is like my rand, I don't want to keep rewriting rand. So I need to solve for x. So I'm solving for x. This is 1 minus u, e to the negative 1/2 x. So this is negative 1/2 x is natural log of 1 minus u. X is negative 2 ln of 1 minus u. Okay, so now I know how to simulate my exponentials. Let's come over to my Excel file. How long does person 1 spend at the ATM? So let's do one trial. Well, they spend an exponential amount of time, and this is going to be negative 2, equals negative 2 times ln of 1 minus rand. That's what I just figured out right there. So there's a sample from the exponential distribution. That's how long my person 1 spends. Person 2, I said same amount of time, right? Gamma's sum of exponentials, so I'm summing up. How long does person 2 spend? Well, equals negative 2 times ln of 1 minus rand. And same with person 3, equals negative 2 times ln of 1 minus rand. And how long is my weight? Well, I need to sum. Okay, so this is one sample, right? This is one trial. I went to the ATM, 3 people were ahead of me. I had to wait 2 minutes. Okay, let's say I do that again. So let's just copy and paste. Okay, so the next time I did it, 3 people were ahead of me. I had to wait 8.9 minutes. So I can generate my own sample of data, which is basically trials of me going to that ATM, seeing there are 3 people ahead of me, and seeing how long I have to wait. So I think I have 1,000 input. So let's go down here. Let's do it for 1,000. Okay, so what you basically have created for yourself is a data set. It's got 1,000 observations, and each of these observations represents you going to that ATM, seeing 3 people ahead of you, and how long you had to wait. Agree?
Yep.
So how do I figure out this probability that my wait exceeds 8 minutes? I count. Yeah, I count. I could do a histogram plot, I could make my CDF, or I could say, well, I really only care about 8 minutes, so let me just focus it on this one. And I'm just gonna count if the number of times in this data set I see something 8 minutes. And that frequency of occurrence translates into the probability my gamma distribution is greater than 8 minutes, the probability I had to wait greater than 8 minutes, and it's about 0.2. If you press F9 and get new samples, it'll fluctuate a bit, but it's around 0.2. So it's around 20% of the time that you have to wait more than 8 minutes.
So in this case, you do have to do 1 minus rand.
Yes. No, you don't. If I just did random, it would be exactly.
I kept getting like 0.4.
It should be right here. If instead of doing 1 minus rand, you did -2 times ln of rand, that should be the same formula. But let me debug that.
Oh wait, I was doing.
And what's the overall lesson here, right? So I think I'm certainly happy for you to complain that my example is a little bit contrived. But what you have seen is something pretty powerful, which is anytime you're working with continuous distributions and you need to understand how to calculate probabilities for them, you know how to do that. Simulate them. If you can identify a sum, that's a really nice way to work with them. So it's really this methodology of simulating the continuous distributions. This is basically a very simple Monte Carlo simulation that we built for ourselves. And we used it to calculate this week. And I will post my spreadsheet after class, so and if I go to what I'm thinking of, my goals for the day.
Could you use the distributions in Excel, like the
Oh, that's a good question. The gamma is built into Excel? Okay, so can I use the distributions built into Excel? So we could go to data analysis. There should be a random number generation. Random number generation, okay. And gamma is not actually built into my Excel.
Oh, I mean if you just type in like equals gamma dot this.
Oh, I don't think it's, okay, it's not giving you, if you I type in equals gamma, that's not giving me a sample from a gamma distribution. There's also the gamma function.
Oh.
So I believe Excel is giving you the gamma function, not a sample from the gamma distribution, and they're 2 different things. But had that been on the data analysis, one of the distributions under random number generation, I completely agree that would be exactly what. Oh, okay, so that would do it. Good. Okay, and so my purpose in this class is you now have a table of distributions. When you do histogram plots, you can form match between, I think we had 8 total distributions, how your histogram looks in 8 possible different distributions. There's a little bit of art there because you're interplaying between both what does that PDF look like and what does this data represent. So what is this situation in the back of my head and does it kind of mean what the distribution means? You've seen this exponential Poisson relationship, and we're getting reasonably comfortable with simulating from continuous distributions. Okay? So you should be getting reasonably comfortable with simulating distributions. So next class we're going to talk a little bit more about summing. Summing comes up a lot, so I'll give you a few more examples for that. I hate to say have a good weekend on a Wednesday, but I won't see you on Monday, so